All right, let's take a trip, not just back in time, but all the way back to the very first second of the universe. We're going to find out how the building blocks of, well, everything were forged.
So, what did the universe even look like 1 second after it was born? I mean, you've got to forget stars, forget galaxies. We're talking about a time before atoms even existed. Just try to picture it, a chaotic, searingly hot soup of pure energy and all sorts of exotic particles. It's a state of matter that's so extreme it's almost impossible to wrap your head around.
Our whole story unfolds in a flash. It's this rapid-fire countdown where the fate of the entire cosmos gets decided in literally less time than it takes to blink. We're going to hit these 4 key moments you see here, and by the end, you'll understand exactly how the recipe for all matter was written.
All right, first up, the Great Confinement. Let's dive right in. So, picture this. The universe is just 30 times seconds old, and as it cools, something dramatic starts to happen. The free-for-all, the wild party for the most fundamental particles, the quarks, well, it's over.
For the very first time, these quarks that were just zipping around freely are suddenly captured. They get bound together by the strong nuclear force, forming brand new composite particles. And we call these particles hadrons. This, right here, is the first real tangible matter in the universe.
Okay, so these new hadrons, they basically come in 2 families. On one side, you've got the sturdy ones, the baryons. These guys are built from 3 quarks, and they include the protons and neutrons we all know and love, the stuff that makes up pretty much everything. Then, on the other side, you have the mesons. They're made of a quark and an antiquark, and they're super unstable. Here one moment, gone the next.
But wait a second, here's where it gets really weird. If you actually add up the mass of the 3 quarks that make up a proton, you only get about 1% of the proton's total mass. So where in the world is the other 99% coming from?
The answer is just, it's incredible. It's not more stuff, it's pure energy. The other 99% is the immense binding energy from the gluons. Those are the particles that carry the strong force. I love this taffy-like analogy because that's what they do. They stretch between the quarks, holding them hostage. So get this, most of what we think of as solid matter is actually just the pure energy of this force.
Okay, moving on. As the universe keeps expanding and cooling down, things get violent. A massive period of annihilation kicks off. All the heaviest, most unstable particles just get wiped out, leaving only the toughest survivors behind. So, if we could pause time at 100 microseconds and just take a quick census of the universe, this is what we'd see. It's almost all lightweight particles and pure energy. I mean, look at this. For every single proton or neutron, there are billions of photons, neutrinos, electrons, and their antimatter partners, positrons. Real stable matter is just incredibly rare at this point.
So what's going on? It's pretty straightforward, really. The universe is cooling down, which means there just isn't enough raw energy to create those heavier, unstable particles anymore. And if you can't make them, they decay and disappear. It's like the universe is cleaning house, just simplifying everything.
And this happens in a kind of cascade. The temperature drops below a certain point, and boom, the pions are gone. They just decay away. A few microseconds later, the muons, which are a little lighter, they vanish too. It's the ultimate cosmic survival of the fittest, and only the most stable particles are left in the game.
All right, let's jump forward to the 1 millisecond mark, because this is where things get really interesting for our survivors. The protons and the neutrons. They're about to start this frantic game, kind of like tag, where their actual identities are on the line.
Imagine a cosmic pinball machine. In all that intense heat, you've got electrons and positrons just constantly slamming into protons and neutrons. Now, if a high-energy electron hits a proton just right, the weak nuclear force can actually flip one of the proton's up quarks into a down quark. And just like that, poof, the proton becomes a neutron. And of course, this whole thing can happen in reverse too. So at first, this back and forth happens at pretty much the same rate. A proton becomes a neutron becomes a proton, over and over. And the result? You get a nearly perfect 1-to-1 balance, 50-50 protons and neutrons. But there's a catch. A tiny one, but it changes everything. A neutron is just slightly heavier than a proton. I'm talking a fraction of a percent, an almost ridiculously small difference. But this tiny bit of extra mass, it becomes the single most important detail as the universe keeps cooling. This is the thing that's going to tip the scales for the entire cosmos.
Because as the temperature drops, there's just less energy to go around. And since neutrons are a bit heavier, making them from lighter protons becomes an uphill battle. It takes more energy. But the reverse reaction, turning a heavy neutron into a lighter proton, that's easier. So, naturally, the balance starts to shift, tipping heavily in favor of protons.
And this brings us to the climax. We're at the 1 second mark now. The universe has expanded so much that all of a sudden, the particles are just too far apart to keep playing this conversion game. It's like the music just stops and the game is over.
See, the weak force that drives all this has a really short range. So as space itself stretches out, the neutrinos and electrons that are zipping around just can't reach the protons and neutrons anymore. That frantic game of tag just stops, cold.
Physicists have a great name for this moment. They call it freeze-out, and that's exactly what it is. It's the point of no return. The ratio of particles gets locked in, frozen in place. The final recipe for all the matter in our universe is now set in stone.
And here it is, the final score, the number that will dictate the entire future of the cosmos. When the game ended, the ratio was locked in at 13 protons for every 3 neutrons. And let me tell you, this is not just some random number. It's the blueprint for absolutely everything that comes next.
I know, 13 to 3 might seem random, but it's the very reason our universe looks the way it does. This specific ratio means we get a ton of hydrogen, which, is the fuel for stars, and just enough of the other ingredients to build heavier elements later on. If that ratio was different, we might be living in a very different and maybe totally empty universe. This thin excess of matter isn't just what we ended up with, it's literally all the matter that will ever exist.
So there you have it. After just 1 second, the stage is set for the rest of cosmic history. The proton-neutron ratio is frozen, ready to build the first atomic nuclei. You've got tons of electrons still zipping around. They'll be important later for making atoms. And the whole universe is just flooded with photons and neutrinos, the leftovers that will one day become the cosmic background radiation we can still detect.
Just think about that for a second. The recipe for matter was written. The fundamental composition of our entire universe was decided in less time than it took me to say that sentence. It's just mind-blowing.
So the raw materials were there, locked in place. But could they ever actually build anything? I mean, the universe was still this searingly hot, incredibly violent furnace. The journey to building the first atomic nucleus, well, that was really just getting started.